Hello everyone. Let's know more about the carbocations with special focus on their stabilities. Basically, carbocation is a trivalent carbon species with a net positive charge. In other words, a carbon bearing 3 bonds with a positive charge. That is, carbon attached to 3 covalent bonds and carrying a positive charge is called carbocation. This is simple methyl carbocation. If you look at the geometry, it is having a trigonal planar geometry with a hybridization of sp2 and bond angle of 120 degrees. As it is sp2 hybridized, naturally it will have an empty pure p orbital. Therefore, it is not having octet of electrons, it has only 6, that is sextet of electrons. That's the reason why it is electron deficient. Therefore, carbocation is electron deficient, will have electrophilic character. Now let's move on to the stability of carbocations. What are the different factors that will influence the stability of carbocations? Because it is one of the most important reactive intermediate in reaction mechanism. So carbocation is positively charged. So therefore, any factor that will disperse the positive charge will naturally enhance the stability. So therefore, electron releasing groups will stabilize, whereas electron withdrawing groups will destabilize carbocations. So let's move on to the groups that will stabilize the positive charge on the carbon. So most important and the most common effect is inductive effect, that also accompanied with hyperconjugation. The most popular groups that exert both inductive effect and hyperconjugation are alkyl groups. So we know alkyl groups will exert plus I effect. They will release the electron density through sigma bonds, and also they will have hyperconjugative effect. So therefore, greater the number of alkyl groups, higher will be the stability. That's the reason why here you will have 3 methyl groups will release the electron density through sigma bonds, that is by means of inductive effect. At the same time, for example, if you take tertiary butyl carbocation, it will give 9 resonance structures by means of what is known as hyperconjugation. That is 9 hyperconjugative resonance structures. So because of that one, tertiary butyl carbocation is more stable when compared to secondary, which is more stable than when compared to the primary carbocation. Now, moving on to mesomeric effect. So there is adjacent pi bonds will always disperse the positive charge present on the carbocation. That is, the positive charge will be moved away from that electron deficient carbon. That means that positive charge is shared by more atoms by means of conjugative mechanism. So therefore, higher the number of attached pi bonds, higher will be stability of the carbocation. Look at here. So this positive charge is adjacent to the pi bond. So we have the positive charge is delocalized over these 3 carbon atoms. So therefore, when compared to the normal carbocation, this is more stable. That is, conjugated carbocation is more stable. If you look at the benzyl system, it will have this positive charge will be dispersed over the entire ring in addition to this carbon. So therefore, benzyl carbocation is exceptionally stable. That is, benzyl carbocation is more stable when compared to the allyl carbocation, which you have seen just now. That is, now look at this one. So here there is no conjugation. Here only you have inductive effect and also hyperconjugation. Here you have this conjugation. Therefore, this is more stable. Here you look at, this is again more conjugated, this benzyl system. These we call them as allyl systems. That is, the positive charge is present on the alpha carbon of the pi bonded system, that is alkene carbons. You call it as allyl system. That is, then if the phenyl group is attached to the carbocation carbon, you call it as benzylic system. So benzyl is more stable when compared to the cyclopropyl and cyclohexyl methyl carbocation. This is simple. You can say this is alkyl carbocation, this is benzyl carbocation. This is again allyl carbocation, this is simple alkyl carbocation. So allyl is more stable when compared to alkyl, and benzyl is more stable. If you compare allyl and benzyl, benzyl is more stable. Adjacent heteroatom. So usually what are the heteroatoms we'll encounter in organic chemistry? Could it be nitrogen, could it be sulfur, could it be oxygen, or even halogen? So all these heteroatoms will have a lone pair of electrons, one or more lone pairs. If you take nitrogen, one lone pair. Oxygen, you have two lone pairs. If you take halogen, you will have three lone pairs of electrons. So therefore, if these heteroatoms are present adjacent to the positively charged carbon, that is carbocationic center, that is very much stabilized due to what is known as conjugation, or you call it as mesomeric effect. Look at here. This is why this is more stable when compared to this one, because this is adjacent to this one. What happens if the adjacent heteroatom is there? Look at here. This carbon is not having octet of electrons. Once you write the resonance structures, look at here. The carbon also acquired octet, nitrogen also having octet. So you may be having doubt. How come the electronegative nitrogen or oxygen or halogen can accommodate positive charge? When these heteroatoms have octet of electrons, then they can accommodate the positive charge, particularly doubly bonded nitrogen, oxygen, or halogen is stable when compared to the singly bonded heteroatom with a positive charge. So what do you mean by this one? Suppose if you take, this is also having, say for example, now this is also having positive charge. This is not stable. That is, the oxygen, singly bonded oxygen with a positive charge is not stable. That's the reason why this will undergo the elimination. Alcohols will undergo elimination reactions in acidic medium, because protonated alcohol will lose H2O molecule, giving out the carbocation. So whereas doubly bonded oxygen with a positive charge, nitrogen with a, here this is more stable, where this one is not stable. So keep these things in mind. Similarly, you can take sulfur also. So this is actually acylium carbocation is very much stable. So due to this resonance, even this is also more stable. I mean, triply bonded oxygen atom. Like this is already, we have seen iminium ion. So oxonium ion is very much stable. So these are some more examples. Even the heteroatom, why? Because here you can say why benzyl is less stable when compared to this one. Even though it will have more resonance structures, only resonance structures is not the criteria. While you are writing resonance structures, this will lose its aromaticity. Look at here. Once you write the resonance structures, I am writing the state I am taking the resonance structure. So, for example, so I'll take this one. So naturally, you will get a positive charge here. Look at here. This system is no more having the, what you call it as, sextet of electrons as such, if you can look at, that is aromaticity for time being. this aromaticity is lost. So therefore, that's the reason why, even though you can write 3 more structures, this is less stable when compared to this one. So try to keep this in mind. These systems are more stable. That is, when the carbocation is adjacent to heteroatom, that is more stable than your benzyl and allyl systems. Next, for example, so what is the correct stability of the given carbocations? What is the, so naturally, here you take the help of the electronegativities. Naturally, sulfur is less electronegative than nitrogen, than oxygen. So therefore, this should be stability of this one should be more than this one, So here both inductive hyperconjugation and this pi donor ability, you call it as pi donation ability of the heteroatom, pi donor capability. You have to take care of all these 3 aspects: inductive effect, hyperconjugation, and pi donor ability. Looking at this, here you don't have pi donor ability. So therefore, so naturally you have pi donor abilities in 1 and 3 structures. So first, naturally stability of 1 and 3 must be more. But here you look at, this is tertiary carbocation adjacent to heteroatom. This is secondary carbocation. So naturally 1 should be more stable than 3. 1 should be more stable than 3. So there is only one option. Then coming to 2 and 4, this is secondary, this is primary. So therefore 2 is 4, greater than 4. Yes, that is the answer. Like that you need to answer. And remember one more factor, the cyclopropyl groups, not only aryl groups, not only vinyl groups, that is allyl systems and benzyl systems, even cyclopropyl groups will extensively stabilize the carbocations, because the cyclopropyl group is highly strained system. So therefore, that will have in fact banana type of bonds, that is weak bonds, which can overlap with the MTA p orbital of the carbocationic center. So therefore, they will stabilize the adjacent positive charge. Yes. So banana type of bonds will interact or try to overlap with the MTP orbital of the carbocationic center. So therefore, some type of conjugation. In fact, if you can look at cyclopropyl methyl, just I will explain. It's called as Homo allyl, will result into Homo allyl conjugation. What is Homo allyl conjugation? Basically, if there is no sp3 carbon in between, this will become allyl. So this is allyl. This is allyl. So in between the carbocationic center and this pi system, one sp3 hybridized carbon is there, one sp3 carbon is there. Such a type of system we call it as Homo allyl system. Homo allyl system that will also stabilize the carbocation like this. So this is Homo allyl type of system that will also stabilize. So therefore, cyclopropyl methyl carbocations are very much stable. They are more stable, even that more stable than the allyl systems. Yes. If we take tricyclopropyl methyl carbocation, also called as, yes, that is more stable than even propylium carbocation, which is aromatic species. Then quite naturally aromatization. So anywhere, if some species, could it be a molecule, could it be a radical, I mean, could it be a charged species like a cationic or anionic, if it is going to acquire aromaticity, definitely that is going to have more stability. So therefore, aromatization will enhance the stability. Let's look at here, propylium carbocation. This is naturally this aromatic system. This is aromatic system. This is aromatic system. Cyclic, conjugated, planar, with 6 pi electrons, with 2 pi electrons. This is also aromatic. This is also aromatic. This is cyclohexadiene cation, also popularly called as propylium cation. In fact, even sometimes benzyl carbocation will rearrange to propylium carbocation. for extra stability. Even hybridization will also influence the stability of carbocation. We know, so sp3 hybridized carbon will have more S character, whereas sp hybridized carbon will have, sp3 will have about 25% of S character, whereas sp will have 50% of S character. So more S character means more electronegative. So electronegative means it can, its ability to accommodate positive charge will decrease. So that's the reason why the stability decreases from going from sp3 carbon to sp to sp2 to sp carbon. So therefore, vinyl carbocation is less stable when compared to the alkyl carbocation, which is even this ethynyl carbocation is further less stable when compared to the vinyl carbocation. But exactly reverse is true with the carbanions, where because their carbanion means electron-rich species, you will have to accommodate negative charge. So therefore, so more S character means more electronegativity. More electronegativity means better accommodation capability of that carbon. That's right. So look at the whereas aromaticity will stabilize the carbocation, the exact opposite thing will happen for anti-aromaticity. Anti-aromaticity will destabilize the carbocation. But that's the reason why whenever there is a possibility of formation of anti-aromatic species, that is least preferred. If you want to leave, abstract this proton, it will give carbanion that is easily found because it will be aromatic. But if you want to remove this hydrogen as hydride, it will result in, or you take some, instead of H, you take some X, you want to pull off that halogen, it will not give. Why? Because the species that is cyclopentadienyl carbocation, which is going to be formed, will be having 4 pi electrons, which is anti-aromatic, which is not at all formed. Yes, whereas anion could be easily formed because aromaticity. So this is the general order. The tropylium cation is more stable when compared to the triphenyl methyl carbocation. So further decreases in this order. Allyl carbocation is less stable compared to the benzyl. This experimentally, that is hydride ion affinity values will also reflect the carbocation stabilities. Look at here. So less hydride ion affinity values means more stable. Means if it is more stable, it will not be attracting the hydride ion again. So therefore, more HAA values means less stable. So it is inversely proportional. Look at some carbocations. This is tropylium carbocation 201 HA. So therefore, so it will have less HAA value. Look at here, this methyl carbocation least stable. So therefore, least stable means more HAA value. So you need not remember, but this will give an idea about the trends of carbocations. Tropylium greater than triphenyl methyl, greater than cyclopropyl cation, then diphenyl methyl cation, then arbonyl system, bridge system, tertiary butyl, then benzyl, isopropyl, then have this is butyl, then have this is again allyl system, then this you call it as, so you look at the difference between this one. This is also going to be in conjugation with the positive charge, but less stable because the carbon is more electronegative. Okay, so these are some species with the different HAA values. And remember, even though tertiary bridged carbocation is particularly in small ring systems, will never formed. So why? Because so the what you call as carbocation demands the planarity. At bridge head, it is very difficult to be you cannot attain the planar conformation. So therefore, in smaller rings, at bridgehead carbocation could not be formed. So this is one important aspect. However, if the ring size is more, the carbocation, that is positive charge, could be formed. If you compare this and this one, this is having little bit more flexibility. So therefore, when you compare this and this one, this is more stable. Like going on, this also, in fact, this is a corollary of a Brett's rule. What a Brett's rule? Brett's rule says that a double bond is never formed at a bridgehead. So like this here, look at here. This has more flexibility. So therefore, this is formed. So from strained rings to flexible rings, carbocation or positive charge could be formed even at bridgeheads in flexible rings. But in smaller rings, carbocation, that is positive charge, is not formed. Look at here. So which is more stable naturally? So bridgeheads, the positive charge at bridgeheads is not at all stabilized. So therefore, simple tertiary butyl alcohol, this is more stable, one is more. Then flexibility is more in this. So 1 is greater than 2 is greater than 3. This is the answer. Right. Next. Yes. Remember, SN1 reaction means the first step, the ionization. Could it be alkyl halides, even the dehydration of alcohols? The first step is the formation of carbocations. So therefore, so whenever SN1 comes into your mind, or even solvolysis comes into mind, or even mechanism comes into mind, you think of carbocation stability in terms of carbocation stability. So these are some examples we can. This we have already discussed. So what is solvolysis? Many will sometimes they'll give which of the following substances more reactive in solvolysis reaction. Solvolysis reaction is again a nucleophilic substitution reaction in which the solvent will compete for the external nucleophile. That is, solvent itself will act as the nucleophile. That we call it as solvolysis reaction. Look at here. So as we are moving from, so just to think of, remove the Cl as Cl minus and try to imagine there is a positive charge in place of this one. So as the that is carbocation stability is increasing from top to bottom, the rate of solvolysis is increasing. Look at here. Primary carbocation, secondary, tertiary, allyl, again allyl with more carbons. Then this is again allyl with more carbons, because once you write the carbocation center here, you will get positive charge. There once again, these methyl groups will stabilize further by means of inductive effect and also hyperconjugation. So therefore, so this is more and more reactive. Look at here. Why the solvolysis rate is more? This is almost 10 power minus 10, almost not at all reactive. Not at all reactive. So therefore, this is flexible. Just now I have given the reason. So this is strained bridge system. Carbocation could not be found because solvolysis means you will have to imagine the presence of positive charge here that could not accommodate. So therefore, stability of this one is more than this one. So naturally, rate is more for this than this one, like that. Just now I have been telling. This Brett's rule means a bridgehead will never accommodate a double bond. So here, so what is the correct order of stability? Yes. Why? Because here this is bridged. So immediately look at the non-bridged system. This is so naturally V is greater than 2 atoms. The 2 heteroatoms are there. This is B is more than C. So this is bridged system. Even though it is having 3 heteroatoms, it is a bridged system. So therefore stability is less. Yes. So based on the discussion which you have done so far, this is the conclusive picture of the various popular carbocations that we encounter in various examples, in reactions and also these are the most popular species that could be given, leaving aside these bridge systems. These are the most popular carbocations. That's triphenyl, tricyclopropyl methyl carbocation, then cyclopropyl methyl carbocation, then triphenyl methyl, diphenyl methyl, tertiary, then benzyl, allyl, then secondary and the primary, finally methyl carbocation. Try to remember this. This is the empirical order only based on the observations. And Marconi-Kaffer rule, what is Marconi-Kaffer rule? The negative part of the addendum will be added to the carbon bearing less hydrogens. Why? This is again based on the intermediate carbocation. So you can say the Marconi-Kaffer rule like this also. The addition to an unsymmetric alkene will take place by an unsymmetric reagent in such a way that the most stable carbocation is formed once, because this is rate determining step. Once carbocation is formed, naturally the corresponding product will be formed. See here, this is primary carbocation, this is secondary carbocation. Why? Because H can add over here or here. So if it is adding over here, you are getting a secondary carbocation that is formed more. So naturally, this is the product resulting in the Marconi-Kaffer product. Similarly, even in elimination reactions, Zaitsev product is formed. Why? Because some 1-2 shifts, we call them, as whenever some less stable carbocation is formed, if there is a possibility of further stability, so naturally the shift of alkyl groups will take place. 1-2 shifts we call them. So these 1-2 shifts of alkyl groups will result in more stable products. That's the reason why in E1 elimination you will expect the rearranged products. So look at here, which is more stable naturally adjacent to the heteroatom. You can say this one, but this is adjacent to this heteroatom. Immediately you can have a conjugation. Here this is not possible because this is multiple bonded heteroatom. So will not stabilize this positive charge. So this is more stable. Look at here, which is more stable. So quite naturally, this is more stable. So here, some of the electron density will be taken away by acyl group. It is NH2, this could have been more stable. Look at here, quite naturally, this is more stable, third one. So this you can work on. Yes, where is if you can look at this will be more stable, tertiary. So simple. Look at here. So naturally 2 is greater than 1, greater than 3. Why? Because this is deactivating group, destabilize. The acyl, suppose if the carbocation is, this is this. Look at here, methoxy group will, look at here. This is stabilizing by resonance. Whereas here, this will be polarized this way, giving further positive charge. So therefore, will be destabilized. This is inductive on hyperconjugation. So therefore, naturally, so 2 is more stable than 1 than, right? Once again, so more stable will be this one. Then again, most stable. These are electron withdrawing groups. So without electron withdrawing group, this is the one. Then here, more stable. Again, heteroatom adjacent. So quite naturally, 3 is most stable. Sometimes they'll ask, compare. So this one and yes. Here you look at this total group will act as minus I effect, exact minus I effect. So therefore, this is not at all stable. Again, propylium. So this is again simple to answer. In each case, quite naturally, tertiary. So here again, adjacent to this, in fact, this group will exert, this total group will exert minus effect. Remember. If positive charge were to be here, suppose if the positive charge were to be here, it will stabilize. It will stabilize. But if it is adjacent, so this total group will exert minus effect. Try to remember. If the heteroatom is directly attached to the positive charged carbon, it will stabilize. Okay. So therefore, so this is tertiary. Remaining things are same. So then, like that you can. So adjacent, it will be having more. It will be having more stability because of the conjugation, like that you can work on. Let's move on. So these are the questions appeared in previous JOM examinations. So species that will not give precipitate on warming with aqueous silver nitrate. We know silver nitrate means it has, the silver ions have a lot of affinity towards the halogens. So you should imagine that is Rx, that is RBr, this plus Ag will give you R plus. So imagine in each case, imagine, in fact, this is gate question, I think. In each case, a carbocation. Look at here, the carbocation. This is again carbocation. Look at, this will give you the anti-aromatic species. This is aromatic. If you can look at, we have discussed this. This is aromatic system. This is aromatic system. This is aromatic system. This is anti-aromatic. So therefore, C is not formed. That is your answer is C. So again, carbocation stability incorporating the aromaticity concept. This again, because this is the Lewis acid again will pick up this halide, that is Cl minus. So again, positive charge is formed over here, positive charge is formed over here. So this will form aromatic species, this will form anti-aromatic species. So this will form aromatic species. Yes. So benzyl, this is Bridger system, Narbonne system, tertiary, allyl. So naturally, benzyl is more stable. So one is more stable. Then comes so tertiary 3, then comes allyl, and the least these two. So 1, 3, 1, 3, 4, 2. This is the other way. Okay. So you try to apply all the things. Here conjugation is given, bridgehead, that is Bret's role is taken care, and also hyperconjugation. This is again the same thing. Solvolysis means think of the positively charged species plus anti-aromatic plus aromatic plus benzyl. So you'll get tropylium plus, you remove this Br and assume the tropylium cation. So 2 is more stable, then 3, then 1. So 2, 3, 1, where is 2, 3, 1? 2, 3, 1. Right. So this is something about the stability of various carbocations. And in next video, we'll discuss about the carbanions. And after that, we'll discuss the reactions involving these reactive intermediates. And regarding stability of free radicals, carbons and nitrogens, you don't have much to discuss. Only you need to discuss about their reactions. Okay, thank you very much.